In this lecture, we're going to talk about polar organic functional groups and how increasing the oxidation state of carbon has an effect on the physical properties of the molecule. So we've already seen hydrocarbon functional groups including alkanes, alkenes, and alkynes that have carbon-carbon single, double, and triple bonds and carbon-hydrogen single bonds. The new functional groups that we're going to look at are going to contain heteroatoms, and a heteroatom is anything other than carbon or hydrogen. So for example, nitrogen, oxygen, sulfur, or halogen such as fluorine, chlorine, bromine, or iodine. Functional groups that contain these elements are typically called polar functional groups because each of those elements has at least one lone pair of electrons, and that serves to polarize the covalent bond to carbon, thereby leading to a dipole moment. And so these things drastically affect physical properties. So what we're going to do is first look at, we're going to compare methane to water on the temperature scale in degrees C, and we're going to look at some of the properties present on the molecular level and how that affects melting point and boiling point. Then we're going to get into oxidizing carbon, and we're going to see through that exercise that we proceed through the different functional groups. And then we're going to look at some complex molecules where we identify specific functional groups within the molecule itself. So our key concepts and lecture learning outcomes. So upon completion of viewing this lecture, you should be able to identify and name common functional groups present in organic molecules, determine the oxidation state of a carbon bearing a heteroatom, assign partial positive and partial negative charges to a polarized covalent bond in a functional group, draw a bond dipole moment for a polar covalent bond, define the terms related to carbon oxidation and reduction, rationalize why functional groups change the physical properties of melting point, boiling point, and solubility, classify alcohols as primary, secondary, or tertiary, classify amine nitrogen atoms as primary, secondary, or tertiary, classify amides as primary, secondary, or tertiary. So on our first slide here, to understand the big picture of what we're doing, let's consider comparing the physical properties of methane versus water. So methane is CH4. Water is H2O. So the melting points of these substances in degrees C are the following. Methane melts at negative 182. Water melts at 0. The boiling points, methane boils at negative 161. And water boils at 100. So we can see from our temperature scale that on the lower portion is in Kelvin, so absolute 0 is 0 Kelvin. So that corresponding temperature in degrees Celsius is negative 273.15. Then we can see at 0 degrees, that's where water freezes. So we see that there, water freezes at 0. It then boils at 100 degrees. So typically room temperature is about 25 degrees C, so that's where we're comfortable, our ambient temperature on human skin. So we're really familiar with 0 degrees and 100 degrees. So if we look at the melting point of methane, negative 182, that's around here on this scale. Then the boiling point, so we're moving this way. When it melts, this is the period between which it's a liquid. So it's going from solid to a liquid, then around negative 161 it boils, and then moving this way it's a gas. So at room temperature, methane is a gas. So for water at room temperature, water is obviously a liquid. So let's look at the Lewis structures of these and see if we can determine what properties they have that give them these vastly different melting and boiling points. So the Lewis structure for methane. So again, the carbon H bonds that are aligned lie within the plane of the screencast. The bolded bond shown here is coming out towards you, and the dash bond is going away from you. So let's go ahead and draw water now. I'm going to put the OH bonds in the plane, and I'm going to actually show the lone pairs just with the wedge and dash so that we can see the molecular geometry. So we see that each of these central atom, carbon, oxygen, has 4 things around it, right? So carbon has 4 H's, oxygen has 2 H's, and then 2 lone pairs. So really it's the presence of these lone pairs that make these physical properties of water so much different than methane. So we recall that the electronegativity difference between carbon and hydrogen is really not that great. So methane is a non-polar molecule. So how does that impact the physical properties? So really, if you consider 2 molecules of methane, there's really no attractive forces between them. So again, at 25 degrees C, it is a gas. So there's really no attractive forces. As you take temperature out of the system and you decrease, that's eventually when you hit the liquid phase. And so when it's in the liquid and solid phase, basically what we're dealing with is dispersion forces, so attractive dispersion forces. And again, that's just the movement of electrons that induce small dipoles. So why is water so much different? So if we look at now the oxygen-hydrogen bond, those bonds are now polarized because the difference between oxygen and hydrogen electronegativity is great. So we see that oxygen has lone electron pairs, so we can say oxygen's partially negative, hydrogen's partially positive. So that bond overall, we can draw a dipole for that bond going this way. The same thing for this OH bond that has a dipole. And then these lone pairs are obviously negatively charged. So basically, the molecular dipole, we'll draw in red here, would sort of go this way, right? So the molecule has a permanent dipole, so it is a polar molecule. So obviously there's dipole-dipole attractions, and so how would we draw that? So if we consider just a dipole-dipole attraction, again, the cross is sort of the plus end, the arrow is pointing to the negative, so if that was a molecule, it would be attracted like that. So negative is attracted to positive. So that's an attraction. So that attraction means 2 molecules are closer together, and that's why around 0 and below, water is a solid. It melts at 0. Between 0 and 100, it's a liquid, because you have these attractive forces. Only when you hit 100 degrees do you put enough energy into the system that you're able to overcome those attractive forces. The other main thing that water has in terms of attractive forces is called hydrogen bonding. So a hydrogen bond is basically a very weak bond between hydrogen and a heteroatom bearing a lone pair. So how can we show that in water? So there's 2 molecules of water, And in blue, what I'll show is a lone pair is attracted to that hydrogen because, as we saw above, that hydrogen bears a partial plus charge. Oxygen's delta minus, delta minus, delta plus. So if you start thinking of molecules in terms of polarity, and the polarity being based on changes in electronegativity from the periodic table, we can start to rationalize melting, boiling point, and solubility properties of these molecules. And really that's what we're aiming to do is looking at a collection of elements in their normal bonding patterns. Are they attracted to one another based on these inter and intramolecular attractive forces or not? So what we're going to do on the next slide is see how we can start from a simple carbon atom, increase the oxidation state by adding other heteroatoms, look at their functional groups and how they affect physical properties. So in this slide, we're going to start off with a functional group that we've already seen. So we're going to start with the alkane functional group, specifically methane. We saw that the melting point was negative 182. The boiling point was negative 161. Again, I don't expect anyone to memorize physical data like this. If you would essentially be given it, and then you have to rationalize, why it is. So there's no point in memorizing things when you can sort of look that data up. So let me go down this column up to the 3 carbon unit. So 2 carbons. This is called ethane. And again, these alkanes end in ane. That's the suffix of the parent name. The melting point was negative 182. So again, by adding a carbon, the melting point change from methane doesn't change that much. The boiling point is negative 89 degrees C. That changes quite a bit. What about propane? CH3, CH2, CH3. So again, these are condensed formulas where we actually see the bonding pattern. Propane, ANE. The melting point, negative 188. So similar to what we've seen. Now the boiling point does change a little bit. And I say we can rationalize that based on more dispersion interactions present in the molecule. I would say typically you do not want to rationalize things on increasing molecular weight because that's really not how physical properties change. So these molecules are basically what I'm going to call right now at an oxidation state of 0. So I'm going to write that in blue up here. Alkanes are oxidation state 0. So we're going to learn some reactions over the course of this semester and next semester. And so in your book, chapter 10, we're going to learn about radical substitution. And what a radical substitution of an alkane will give you is an alkyl halide. And we're not going to worry about how this happens right now. Basically, what we're going to do is just look at the functional group present and how that functional group changes the melting and boiling point. Okay, so before we do that, just a little mistake here. I wrote methane as CH3. It should be CH4. I apologize for that. So what we're going to do is take methane, and we're going to substitute out a hydrogen for a halogen. So in this specific column, I'm going to use bromine to do that. So if we substitute out a hydrogen for bromine, we get this compound, which is called bromomethane. So how do we understand this? It's a methane derivative, and it has a bromine. So the parent of this molecule is 1 carbon unit. We see that. And bromine is a substituent. So anytime you have a heteroatom, you should always put your lone pairs in. So halogens have 3 lone pairs, and then they have 1 sigma bond. So in the presence of the lone pairs, the electronegativity difference between carbon and bromine is pretty big. So we say bromine's delta minus, carbon's delta plus. So overall, this molecule would have a dipole moment pointing that way. The melting point is now negative 94. The boiling point is 4 degrees C. So again, what do we want to understand? That in substituting a hydrogen for a halogen, look how much the melting point and the boiling point has now changed. And that is due to the presence of these lone electron pairs, the polarized bond. Now we have these dipole-dipole attractive forces. So let's go down and do the same for these alkanes as well. So we're going to substitute out CH3, CH2, again delta minus, delta plus. This is called bromoethane. The melting point is negative 120. The boiling point is now 38. So we're now with this compound is a liquid at room temperature, because if we're sitting at 25 degrees C and it boils at 38, it's a liquid. So you can see bromomethane boils at 4 degrees C. Just by adding a second carbon, it's now a liquid to bromoethane. And that's a huge jump from substituting H to Br in these physical properties, especially the boiling point. So let's now consider propane. So there's 2 things we need to consider, is that when we're moving to propane, this molecule, we have 2 types of carbon now. So what I'm going to do in this space here is show you, if we substitute a hydrogen from this carbon, what those physical properties are, and if we substitute a hydrogen from that carbon, what those physical properties are. So our first compound, CH3, CH2, CH2, Br. This compound, we have to call it now 1-bromopropane. And the logic behind this is, again, it's a 3-carbon unit, it's an alkane. The bromine is a substituent. The 1 is telling you which carbon that bromine is bonded to. So our melting point is negative 110 degrees. Our boiling point is 70 degrees C. So we've basically bumped up quite a bit now. So again, we've substituted an H off that carbon. What about substituting one of these methylene H's? These compounds are constitutional isomers. So now this is a different compound. So the bromine is now at the 2 position, so it's 2-bromopropane. And they're going to have different physical properties. So this melts at -89, and it boils at 59. So in terms of classification, we can say this methyl group is primary. The methylene group is secondary. So therefore we can say this alkyl halide here, it's a primary alkyl halide. This one is a secondary alkyl halide. And again, it's important for us to know how to do this, because when we start learning mechanisms, we can run reactions where we selectively react one over the other based on kinetic preferences. So getting back to this column, so notice we have CH bonds, we have CC-CH bonds in ethane and propane. There's no heteroatoms at all in the alkanes. Now we have a heteroatom. So it's a single heteroatom. So I want to, just in terms of bookkeeping, I'm going to call alkyl halides are at an oxidation state of 1. And the only thing I've done is I just counted how many bonds this carbon has to a heteroatom. It's just 1. It's a sigma bond. So this carbon is at an oxidation state of 1. This carbon is still at an oxidation state of 0. It's a bond to carbon and 3 bonds to hydrogens. So we call that 0. This is 1. This is an oxidation state of 1. This carbon now is an oxidation state of 1. So far we've increased polarity by doing substitution of H for halogen. We're going to learn another type of substitution reaction in Chapter 7. And so these are our functional group substitutions. So once we've gone from a nonpolar molecule to a polar molecule, so this is a polarized bond, we can therefore do substitutions of that group for other things. So the functional group we're going to learn in this column are called alcohols. So an alcohol of the methane derived alcohol has the following structure. So we put in our lone pairs. So this compound is called methanol. So look at the ending, OL. That ending tells you that it has this functional group. OL means it has that functional group, hydroxyl. The hydroxyl group, OH, is indicative of an alcohol, so methanol. The melting point of which is -98 degrees C. The boiling point is 65 degrees C. So at room temp, methanol is a liquid. What about the C2 alcohol? So ethanol, so this is the active ingredient in any type of drink when you're at the bar. Ethanol is the alcohol that makes you feel good. So again, OL is telling you that this OH group is in there. Ethanol. So it's an ethane derivative. It's 2 carbons. Ethanol tells you the OH group is there. The melting point, the boiling point, we're -114. We're now increasing the boiling point slightly. So just like with the alkyl halide, where we had a primary alkyl halide and a secondary alkyl halide, we can have a primary alcohol and a secondary alcohol. The primary alcohol, CH3, CH2, CH2, OH. This is called 1-propane. Now I'm dropping the E and adding OL, 1-propanol. Again, the nomenclature that we're going to learn over the course of this semester. The 1 is telling you where the OH group occurs. So the OH group is at the 1 position, 1-propanol. The melting point is negative 126 degrees Celsius. The boiling point is 97 degrees Celsius. So our boiling points increase quite a bit. So what about the secondary alcohol? CH3, CH, CH3, OH. This is now 2-propanol. Again, the 2 is telling you where the alcohol is located at the 2 position. The melting point is negative 89. The boiling point is 83 degrees C. So again, this is classified as a primary, this is classified as a secondary. And the reason that's important is because these will have different reactivities when we learn functional group transformations. So one other connection between the prior, so we said an oxidation state 1 has a single bond to a heteroatom. So look at this carbon has a single bond. All these alcohols do. So alcohols are also at an oxidation state of 1. So what I want to do is of the ethanol, I want to put in a constitutional isomer of ethanol that is a different functional group. So if you look, the molecular formula of ethanol, so the molecular formula is equal to C2H6O. So the molecule is fully saturated, but we can draw a constitutional isomer of that. That constitutional isomer has the following structure. CH3, now the oxygen in the middle, CH3. So this compound is called dimethyl ether. So the COC functional group is an ether functional group. This has a melting point of negative 141 degrees C and a boiling point of negative 24 degrees C. So how can we rationalize that between these two constitutional isomers, really this huge difference in boiling point? So this is a gas at room temperature, this is a liquid. And when we're looking at this, the main difference is the presence of this OH functional group, which has the ability to hydrogen bond. That means a molecule of this can hydrogen bond to another molecule of ethanol. They're attracted to one another. So it takes quite a bit of heat to put into the system to get it to boil. Notice the dimethyl ether does not have an OH group, so those molecules are not as attracted to one another. So each of these carbons, CO, so that's one 1 sigma bond, that's at an oxidation state of 1. This carbon is also at an oxidation state of 1. So that follows under the oxidation state 1 functional groups. So in this column, I'm going to need to erase this for now so that we can move up in terms of oxidation state to oxidation state 2 now. So I'm just going to erase this. And we're going up to oxidation state 2. And so this is chemistry primarily that is covered in Organic Chemistry 2, CHE 256. However, the functional group names are presented in Chapter 2, so we need to learn them because it's imperative to look at big molecules and know what functional groups are present in them. So the first oxidation state 2 functional groups that we're going to look at, there's 2 of them. There are aldehydes and there are ketones. So what I mean by this oxidation state 2, essentially if we look at methanol, we're going to increase this carbon's number of bonds to this oxygen. So if we do that, we're going to form a pi bond now. And in terms of the oxidation, we're getting rid of a molecule of H2. An oxidation is always an increase in carbon's number of bonds to a heteroatoms. You can also think of it as a formal equivalent of losing H2 from the molecule. So if we do that, we now end up with the following. So again, we've lost this H in one of these H's. This carbon now has 1, 2, so that's oxidation state 2. This is called an aldehyde. An aldehyde has a CO pi bond and a carbon bonded to H. So we have now sp2 hybridized carbon. This molecule is called methanol. So an aldehyde ends in Al. The melting point is negative 92 degrees C. The boiling point is negative 19 degrees C. Let's go ahead and do the same thing for ethanol. If we were to oxidize it, this carbon oxidation state increases. So CH3C. So this collection of atoms here, that is the aldehyde functional group. sp2 hybridized carbon double bonded to oxygen plus this hydrogen. That's an aldehyde. So this becomes ethanol, so it ends in Al. The melting point is negative 124. The boiling point, 20 degrees. For the propane derivatives, it is important to see that this primary alcohol can be oxidized to an aldehyde. The secondary alcohol, when it's oxidized, it no longer forms an aldehyde because you can't have this H group present anymore. So it forms a different functional group, and that's called a ketone. So here's the aldehyde functional group, and this is called Propanal. The melting point is negative 81 degrees C. The boiling point is 46 degrees C. So again, notice what I said in terms of this oxidation state increasing to 2. So you have 1, 2. You're getting rid of this hydrogen and one of these hydrogens. So notice the hydrogen count on this carbon decreases. So it's 2, it's going to 1. This secondary alcohol, it only has one hydrogen. So when it's oxidized, this H and this H go away. So that is a different functional group, and it's called a ketone. Again, notice you have a CO pi bond. There's no H here now. We're at oxidation state 1, 2. This is called a ketone, so it ends with a different name. So it's 2 propane. Now it becomes ONE, ketone, ONE, 2-propanone. The 2 tells you the location of the carbon-oxygen pi bond. The melting point is -95. And the boiling point is 56. So again, we can go another oxidation state up. Again, this is primarily CHE256 material, but the functional group introductions are present in chapter 2 of the textbook. So oxidation state 3. We're going to look first at carboxylic acids. So what are we doing now? Again, we're going to increase the oxidation state of that carbon by 1. So here it's 1, 2. When it increases, it goes to 3. And that oxidation state functional group is called a carboxylic acid. So now this is a methane derivative, so it's methanoic acid. So the methane, the E goes away, we add OIC and then the word acid separated by a space, methanoic acid. Now we're going to see the physical properties change quite a bit. The melting point is at 8 degrees C and the boiling point is now 100 degrees C. Again, notice this trend. We have nonpolar, we're increasing polarity. Nonpolar, we're increasing polarity. Methanol and methanoic acid both have OH groups that can hydrogen bond. Methanol does not. So notice these are two relatively high boiling points, whereas this one is not. And that's due to the attractive forces that the hydrogen bonding allows for. So now we're going up. Again, you always want to put your lone pairs in for heteroatoms. We have ethanoic acid. The melting point is 16 degrees. The boiling point is 118 degrees C. So ethanoic acid is actually the major component in Italian dressing or vinegar. So now for the oxidation of the propane derivative, only this terminal carbon can be oxidized. The 2-propanone cannot. We see that there's no hydrogen bound to this carbon that we can remove to oxidize it. So really, this hydrogen is the only one we can remove to form an oxidation product to give us oxidation state 3. And again, that would be propanoic acid. The melting point, -20. The boiling point is 141 degrees C. So it turns out that there are multiple oxidation state 3 derivatives, and they all have basically what I'm going to call an acyl group present in them. So from the prior slide, we saw the acid oxidation state. Again, this was ethanoic acid. So the CO pi bond in sort of the left part of the molecule, the CO pi bond including that's typically called an acyl group. Acyl group. Now this other part of the molecule in ethanoic acid, this is OH. This can change. So basically we can have other oxidation state 3 derivatives depending on what is located at this position. Again, oxidation state 3, this carbon has 1, 2, 3 bonds to heteroatoms. So the first one we're going to look at is called an ester. So CH3CO, this has a bond to oxygen. Now instead of having an H, if we have another carbon, that's called an ester. So this is the ester functional group. CO pi bond, sigma bond to oxygen, we're at oxidation state 3. This is carbon. This would be named according to naming this carbon first. That's a 1 carbon unit. So it would be called methyl. Then there's a space. Then 2 carbons, ethanoate. So the methyl corresponds to this carbon right here. The ethanoate, OATE, tells you about the rest of this being an ester. Ethane is the 2 carbon unit. The O8 is the functional group ester. Our melting point and boiling point are -98 degrees C. Our boiling point is 57 degrees C. So what if we, instead of having oxygen, what if we have nitrogen present? These are called amides. And there are 3 classifications of amides. Nitrogen has a lone pair. This is called a primary amide. It's primary because the nitrogen is only bound to 1 carbon. Another way of thinking of it is the nitrogen has 2 hydrogens. So the name of this amide is ethanamide. So it ends in AMIDE, ethanamide. This has a melting point 79 degrees and a boiling point of 221 degrees. So that's quite a big jump. So how do we rationalize that? This NH bond, these are basically hydrogen bond donors and acceptors, so there's a very strong intermolecular attractive force between the molecules. So the next type of amide is called secondary. And so the difference is now that we've taken a hydrogen, we've substituted a carbon. So again, we have 2 carbon bonds, so that's where we get the secondary. There's 1 bond, there's 2. The name of this compound, we're going to name the group on the nitrogen, so N-methyl. Then in a single word, ethanamide. So there's the amide ending. The ethanamide part tells you there's 2 carbons. The N tells you that that methyl group is bound to that nitrogen. So N-methyl ethanamide. So it's a 2-carbon amide. The last one is called tertiary. And again, this is going to result from substitution of both groups now to being carbon-based groups. So we have 1, 2, 3 bonds to carbon, so this is a tertiary amide. Both of those groups are now bound to the nitrogen, so we say it's NN-di, there's 2 of them. They're methyl groups, dimethyl ethanamide. The melting point is -20. The boiling point is 156. So it looks like I forgot to put in the melting point and boiling point data here. This was 26. This was 204. And so let's just talk about this trend briefly. Again, this boiling point is pretty high. We now see it decreased. And the reason is because we've substituted one of these H's for a carbon. Now notice this decrease. This H is now gone. We both have carbon and carbon. So this part of the molecule is no longer able to hydrogen bond. So therefore the boiling point decreases considerably. So of the oxidation state 3 derivatives, there are 2 more that we need to know. The first one is called an anhydride. And anhydrides have the following structure. There's a carbonyl or acyl group, bond to oxygen, and another acyl group. So this moiety in the middle, CO pi bond, sigma bond, CO pi bond, this collection of 1, 2, 3, 4, 5 atoms, and that bonding pattern is called an anhydride. This molecule would be called ethanoic anhydride, and it has a melting point of -73 degrees C and a boiling point of 140 degrees C. The last oxidation state 3 functional group is called an acid halide. So we'll look at one of them, specifically the acid chloride. So again, oxidation state 3 is this carbon. We have 1, 2, 3 bonds to heteroatoms. That's where we get the 3 from. Then this is called ethanoyl chloride. So 2 words separated by a space. The chloride is obviously this part. The OYL is this part, ethanoyl chloride. Our melting point is -112, and our boiling point is 52 degrees C. So notice there's really no ability to be a hydrogen bond donor in this molecule, so we have a relatively lower boiling point. So what I'd like to do is circle back to oxidation state 1 derivatives that contain nitrogen. So we've looked at oxygen. We saw oxidation state 1 functional groups were either alcohols or ethers. So what about nitrogen? These are called amines. So amines contain a carbon-nitrogen bond, and there are 3 types or classifications of amines. So there's primary, there's secondary, and there's tertiary. So if we're just going off the 1 carbon unit CH3, sigma bond to nitrogen, NH2, this would be called methanamine. So we're taking methane, we're dropping the E and adding AMINE. The melting point's negative 93 degrees C. The boiling point is negative 6 degrees C. So we call this a primary amine, primary, because the nitrogen is only bound to 1 carbon. As we move down, we're going to successively remove these hydrogens. So a secondary amine, we can draw the following: CH3, 2NH. So now we have nitrogen bound to 2 methyl groups. So that's secondary. We're decreasing the hydrogen bond capability. And so what about a tertiary amine? Now we're going to substitute we're going to substitute all these hydrogens for carbons now, so there's no more NH bonds present. So the condensed way of doing that, CH3, 3N, the nitrogen now is bonded to 3 carbons. This is NN dimethyl methanamine. The melting point is negative 117. The boiling point is 3. So I didn't write this name up here. This was N-methyl methanamine. And we're basically naming the extra carbon groups as substituents to the nitrogen. So oxidation state 1 with nitrogen, the carbon is bearing 1 bond to nitrogen. This is primary because there's only 1 CN bond. This one has 2 CN bonds. This one has 3. So primary, secondary, tertiary. That's how we classify amines. So what we're going to do over the next 2 slides is look at a complex, 2 complex molecules with different polar functional groups, and visually we're going to identify what those functional groups are. So as we saw before in the prior chat session, this molecule is called Tamiflu. So what we want to do now in these boxes is identify what functional groups are present. So let's start here. We have an oxygen bonded to 2 carbons. So this is called an ether. Here we have a carbon-carbon pi bond. This is called an alkene. Here we have a carbon-oxygen pi bond bonded to another oxygen. So if we count, that's 1, 2, 3. This carbon is at oxidation state 3. So we have to do a little bit more probing. The group bonded to this oxygen is carbon. So this functional group here is called an ester. And again, what you're looking to do in this exercise is make an association with how these atoms are bonded to one another and what the name is. This box is pointing to this carbon right here by itself. It's an sp3 hybridized carbon. It's at an oxidation state of 0, so we would call this an alkane. This group right here is a nitrogen. So it's an amine. It's an amine bound to one carbon. So we would call this a primary amine. This last group, it's a carbon bound to 1, 2, 3 heteroatoms. So we're at oxidation state 3. We have a CO pi bond, then a bond to nitrogen. So this is an amide. The amide is bound to 1, 2 carbon groups, so it's a secondary amide. So what we've done on this slide is identify 1, 2, 3, 4, 5, 6 functional groups present in Tamiflu. So this molecule is called rapamycin. You can see it's considerably more complex. So let's go ahead and do the same exercise. This box is pointing to this carbon, which is bearing a sigma bond to oxygen, so it's an OH. This has to be an alcohol. It has 1, 2 bonds to other carbons, so this is a secondary alcohol. This box is pointing to this carbon. We have 1, 2, 3 bonds to heteroatoms, so we're at oxidation state 3. We do a little bit more examining. We see that the bond from oxygen to here is carbon, so this collection of atoms would be classified as an ester. This arrow is pointing here. We're at a carbon at oxidation state 2, so we have 1, 2. So again, we're just counting the bonds. We have 1 bond, 2 bonds to oxygen. We're at oxidation state 2. So this would be, if we look over here, oxidation state 2. This is carbon, that's carbon, so this is a ketone. Coming over now to this carbon, there's a single bond to a heteroatom, so we're at oxidation state 1. We have an OH group, so it's an alcohol. This carbon has 1, 2 bonds to other carbons, so this is a secondary alcohol. Now coming over to this box, we have 1, 2 bonds. This carbon's at oxidation state 2. It's bond to carbon and carbon, so that means it's a ketone. This box is pointing to that carbon, It's sp3 hybridized. It's got an oxidation state of 0, so we would say that's an alkane. So we would specifically call it a methyl group because it's bound to 3 hydrogens. Now this box is pointing to a carbon-carbon pi bond, a double bond here. So this is an alkene. This box is pointing to a CH2 group, a methylene group, so that's an alkane as well. Here we're pointing to a carbon that has 1, 2, 3 carbon bonds, 1 H bond, so that's an alkane. And we would classify that as a methine carbon. We're pointing now to a carbon that has 1, 2, 3 bonds to heteroatoms. That's at oxidation state 3. We have a bond to a nitrogen, so it's an amide. We have 1, 2, 3 bonds to carbon. So we would call this a tertiary amide. And then finally, our last box, we're pointing to this oxygen that's bound to carbon and carbon. So this is an ether. So overall in this screencast lecture, we've looked at increasing oxidation state of carbon to get increasingly polar covalent bonds into a molecule and how they affect physical properties, and then looking at how those functional groups are named and then identifying them in complex structures.